Good morning. Here we have a DIN rail mount power supply, and it's made by Wago, W-A-G-O, and it is model number 0720. It's going to replace one that caught fire. Let's open up the box and see what we've got. Comes in a nice box. There we go. Little packet of desiccant. We can use that in future packing. Here's some instructions. Now this is called Eco Power, and it's model 787-032. Wonder what that is on the label on the front. Huh. That must be the series number, 0720. So, on the line side, we have L and N terminals in frame ground, and it says input 110 to 240 volts AC, 3.5 amps, no, I'm sorry, 3.2 amps, 50 to 60 hertz. On the output side, 24 volts DC, and it can source that 24 volts at 10 amps. There's an adjust pot, looks like two LEDs, DC OK and overload. So we're going to hook this up and load it down with a resistor and see how she does. Oh, after this, I'm going to show you how to statically and dynamically test an IGBT, here 7MBR15NF120, made by Fuji Electric. We want to make sure this power module is good before we install it into a drive. That'll be the next video. That'll be a fun one. Let's insert our hookup wire so we can power this drive up. We're going to use 110 volts AC single phase. Now, I don't like these types of connectors. I like the screw terminal connectors. Now these will clamp down on the wire probably much better, but they're really hard to install the wire. What you have to do, there's the round part where the wire is inserted, and then there's a part up here that we have to pry down on to open up that clip. Let me get a flashlight in there and make sure I'm opening it up properly. Yeah, okay, I think I am. Insert our wire, make sure it's installed, and then we'll get the second one. That was the neutral side. We're going to hook up the line side now. Just to me, they're much easier with screw terminals. Now, there's a tool that will allow you to open up these spring clip terminals, but I didn't see the tool in the box. It wasn't shipped with this unit. All right, let me get our line plug here. I'm going to power it up first before we load that output down, just to make sure it powers up. plug ourselves into the wall. All right, good. We got a DC OK LED on. Let's measure the output. Make sure it's 24 volts unloaded. Can y'all see that? Turn that light on. Okay, I'll read it to you if you can't see it. Plus terminal and the minus terminal. And unloaded, we have 24.14 volts DC on the plus and minus terminals. Now, let's power down and we will install a load resistor. I have two parallel 5 ohm resistors right here. And we'll be able to pull about 4 amps, 4.8 amps from that 24 volt supply. Let me tighten up the screws, come loose. Okay, let's get unplugged from the wall. Turn this around so we can install that load resistor. Put it on the next terminal over. That's too close to that metal for my liking. We might short that positive terminal to the metal case. This is metal. Maybe that's plastic. I can't tell. Looks metal to me. So let's put this over on the next positive terminal over. There we go. That's one side of the 5 ohms of resistance. I've got some good clearance right here. We'll go ahead and install the other side of the resistor in that terminal right there. And now we're fully hooked up. We have 5 ohms on the plus and minus terminals. Our green OK, DC OK LED still came on. All right, let's see what our voltage across that resistor is. We're still in the picture. This is the positive side over here. Okay, we've had just a little bit of a voltage drop, but not bad. We have 23.96 volts DC across the resistor. Let's go see what it measures like up here on the terminals, because we're going to have some loss in the wiring and the resistance. All right, there we have 24.09 volts DC at the terminals. So we have some voltage loss in this wiring. Now, I'm going to go get the ammeter. I have a clamp meter. We're going to see what our current draw is. This is a south wire clamp meter right here. I really like this. It measures DC and AC currents. We'll move this to AC-DC amp meter, and we want to select our mode. Right, it always comes up in AC. So we select a mode, change it to DC, and you see right here, just in the air, it says 0.3 amps. We hit the relative key, and that zeroes out the meter. Okay, now let's see what our current draw is. Look at that. The math is correct. 4.79 amps. 4.8 amps. Can you all see that? And 24 volts divided by 5 ohms is 4.8 amps. We're getting They're getting warm. They are getting warm. If it was wintertime, we could warm up our hands on those resistors. Here we go. That's a good power supply right there. Now, we're going to move on to something more fun. We're going to test this IGBT power module. I like doing this. It will be fascinating. All right, all. We got us a good power supply. It hasn't caught fire so far. Uh-oh. There goes an ambulance up the road. Somebody's having a bad day. Whew. I always hate to see ambulances and fire trucks and police cars go up the road. Somebody's day it just went all to hell. Okay, I hope y'all's having a good day. Be careful out there, folks. Be careful. Let's disconnect our connections. We'll box that power supply up and it will get installed at the factory. Come on. Can't get that one back down. All right. There's the resistor. Oh, hot, hot, hot. There you go. It's a nice power supply. Alright, we're going to use our meter, set the diode test mode to see if we have any opens or short circuits on this IGBT. And its part number is 7MBR15NF120, manufactured by Fuji Electric. Now, let's find the N terminal. Right here's the N terminal, so we're going to put our red lead starting out on the N terminal, and let's put our lead on the P1 terminal. Let's see what we have. There's a diode drop of 0.837 volt. Now, leaving our red lead on the N terminal, we're going to go through and test the B, U, V, and W terminals with the black lead. Oh, don't wiggle around. Okay, B to N, we have no diode drop. Let's go U to N. There's 0.459 volt diode drop. Move our black lead to V. 0.458 volt diode drop. Black lead to W. 0.459 volt diode drop. Now let's put our red lead on P1 and go, let's put our black lead on the P1 terminal and the red lead on the B terminal. There we have a diode drop of 0.459 volt diode drop. Here's your red lead on U, 0.52 volt diode drop. Red lead on V, black lead still on P1, 0.459 volt diode drop. W with the red lead, 0.459 volt diode drop. Now this IGBT also has a three-phase bridge. Let's go ahead and check that. Here's the P and the N terminals. Let's put a red lead on P. Getting my colors mixed up. Black lead on P. Red lead on R. Stay on there. 0.553 volt diode drop. Red lead on S. Black lead on P. 0.550 volt diode drop. Red lead on T. Black lead on P. 0.551 volt diode drop. This IGBT power module checks good with our meter. Now what we're going to do is we're going to connect this to an IGBT tester. And what we'll do is we'll only check one IGBT at a time. In this package, there's an IGBT for the regenerative braking circuit. There's 3 IGBTs for the high side UV and W, the high side being connected to P1. The collectors of the 3 high side IGBTs connected to P1, and the emitters of the high side IGBTs connected to UV and W, the 3 on the high side. Then you have 3 on the low side. The emitters of the 3 low side IGBTs are all connected to the N terminal, and U, V, and W are connected to the collectors of the 3 low side IGBTs. And so you have 2 IGBTs from P1 to N, and 2 more IGBTs from P1 to N, and 2 more IGBTs from P1 to N, and in between the 2 you have U, V, and W. Phew! Now if you saw that, I'll show it to you. When you see that as in a picture, it'll make sense. Trying to say it with words is kind of confusing. But I'll show you my drawings at the end of this video, and you will say, oh, that's what he was trying to say. Why didn't you just show me the picture? Maybe I should have done that. Well, anyways, let's, what we're going to do, oh, I got myself sidetracked. What we're going to do is we're going to only check one IGBT at a time with my IGBT tester, just one at a time. I know there's 7 in here, but we're only worried about one at a time. So let's go ahead and hook it up and we'll see what we can do. Here's our gate driver circuit. I'll show you my schematic drawing of our gate driver circuit when we get done with the video. And let's bring our variac into the picture. Here's our bridge rectifier and our bus capacitors. They're going to make our DC bus voltage. Put these light bulbs down there so I can get this plugged in. Okay. Let's move you guys over just a little bit so we can make room for our load. These light bulbs right here are going to be placed in the collector between plus bus and the collector of each individual IGBT, one at a time. And these will represent the load. We're going to do the low side IGBTs first. So we want to take the load, 2 series light bulbs. We'll go and do the B terminal first. And the ground side of our bus capacitors are going to connect to the N terminal. Okay, everybody's off right now. We're all unplugged, so we're good to go. Now let's power up our circuit right there. We have to have 2 supplies. I have a 555 set up in astable mode, so it's a continuous square wave out of the 555 IC. That drives into an optocoupler right here. The input LED of the optocoupler. The output side of the optocoupler is driving the base of this tip 121 NPN transistor. And the collector of the transistor will drive into the gate of the IGBT. And the gate voltage of this IGBT is plus 15 volts. Now this circuit is a test circuit. I have to stress this. This would not be seen in a drive because we have 2 IGBTs that are totem poled, one on top of the other. And you have to ensure that the opposite IGBT is turned off when the other one is turned on, so that you don't create a short circuit between plus bus and bus ground. So on a drive circuit, a gate driving circuit inside a servo drive or a squirrel cage induction motor drive, they will apply a negative voltage to the gate when it's to ensure that it's turned off, when they apply a positive voltage to the other IGBT to ensure that it's turned on. But a positive gate voltage of this IGBT is 15 volts. So 5 volts to power up the 555 timer IC and 15 volts for the gate driving circuit. Let's tie the grounds of both together. This will be our 5 volts right here. That goes to this terminal. The grounds of the supply go right there. And the 15 volt power supply is connected to this terminal. Now, normally in a drive, the 3 high side power supplies are separate, but since we're only powering up one IGBT at a time, we can connect the drive circuitry to the low voltage, the 555 timer. We can connect the grounds together. But what you would see in a real drive is that the high side IGBTs would have 3 separate power supplies to power up the high side firing voltages. They're not connected together. Now the 3 low side IGBTs, they are connected together. They have a common ground, which is bus ground, the N terminal. Let me turn our scope on here because we're going to need to look at the load firing. Now, let's hook up our gate to the B IGBT. Get my sheet out here so we can get the numbering correct. Hook up our scope to ground. With the gate of the B terminal is pin 7. Okay, that is this one right here. we're going to clip that onto the collector of the tip 121. Now, we're going to connect or ground of the system that we have set up here to pin 11, the E terminal. Now the low side IGBTs that we're going to test are the E terminals connected to the N terminal. So we're going to connect it to pin 11. So pin 11 is connected to the N terminal. If you took your meter and tested continuity from pin 11 to pin terminal N, you would see that they're connected together. Now, we're going to connect our scope probe to terminal B. Let's see what we get. Let's plug our variac in. Make sure it's turned all the way down. Okay, our green light to indicate that we have square waves emitted at the output of that 555 timer. Alright, I've got my scope probe set to times 10. And the scope is set to 10 volts per division. So right now, we have pulses on the B IGBT from peak of 100 volts to ground, to bus ground. You can see our light bulbs have lit up a little bit. We can go a little bit higher. That looks like a peak of 150 volts peak. And we'll get closer to the oscilloscope there in a little bit, and you can see what we have across those light bulbs. But the B terminal, the regenerative braking terminal, is working. It looks good. So before I switch to the next IGBT, I'll turn the variac all the way down. And while the gate is still being turned on and off with the driver circuit, I'll unplug the variac from the wall. And that will discharge the high voltage side. I don't like to float the gate when I move from one IGBT to the next. So what I'll do is I'll disconnect the high voltage and move the gate driver. Let's turn it off. Turn off the circuit up here and move the gate driver. We're going to test the U low side IGBT, and that's on pin 8. So we're going to move the collector of the tip 121 from pin 7 to pin 8, and we're going to move the load light bulbs from B to U terminal. Now, let's plug everybody back in. And we're going to raise that voltage. There's 100 volts peak. About 150 volts peak. So the U low side IGBT is firing correctly. Now what I'm going to do is we're going to move the camera in front of the oscilloscope, and you'll get to see the waveforms at the output of each individual IGBT, switching the light bulb load from plus bus to ground through that IGBT. Here's the waveform at the U terminal, the low side IGBT of the U terminal. And our scope is set to 10 volts per division. And here we have a peak of 150 volts per division. You can go up. You can go up here. There's 200 volts per division. Shoo, be careful there. You don't want to get across that. That'll light you up. So here we're going to move to the V terminal. Let's lower the variac voltage. You can see the DC bus is being discharged. I'm going to unplug the variac, and now the IGBT has pulled all of that energy to ground, so you can see there's no pulses down here. Let's turn off the power supplies to our driving circuit. I'm disconnecting the U terminal. The V gate on the low side IGBT is on pin 9, so I'm moving the collector of the tip 122 to pin 9, and I'm moving the load resistance, the 2 light bulbs, to the V terminal. Plugging the variac back in, turning on the 15 and 5 volt power supplies. You can see there's a little bit of firing right there. There's some voltage on those bus capacitors. Let's increase the variac voltage. Our DC bus is increasing. There's 100 volts per division. There's 150 volts peak right there. Just eyeballing it, it looks like it. Let me bring that trigger point down just a little bit. Let's set it halfway. All right. So the low side V IGBT is working. We'll reduce the AC voltage of the variac. Unplug that variac. Turn off the 15 volt and 5 volt power supplies. Disconnect the light bulbs from the V terminal. Now pin 9 is the one we were on. We're going to move to pin 10. That's the low side W gate of the IGBT. Alright. And we're going to connect the load resistors to the W terminal. Let's plug the variac back in. Powered up the 15 and 5 volt DC power supplies. We're going to increase the voltage with the variac. There's 100 volts peak. And there's 150 volts. Just eyeballing it, maybe a little bit more than 150 volts peak. Low side W IGBT is working. So all the IGBTs, the B terminal, the UV, and W terminals of that IGBT on the low side are working. We're going to go test the high side, the 3 IGBTs on the high side. We're going to do that right now. Let's reduce the variac voltage. Unplug that variac. Turn off the 15 and 5 volt DC power supplies. Now to test the high side IGBTs, we're going to test the U IGBT first on the high side. Pin 1 is the gate, pin 2 is the emitter. So we're going to move the collector of the tip 121 to pin 1, and we're going to move the ground to pin 2. And this is a little bit different. Now the load resistors are going to get connected to P1. P1 is the collector of the 3 high side IGBTs. And we're going to move bus ground to U. Does that make sense? It will make sense when you see my drawings. Okay, let's plug the variac back in. We're going to increase the variac slowly to make sure we're hooked up correctly. Yes, we are. There's 100 volts peak. And there is about 150 volts peak. So the U high side IGBT is working. It is good. Let's reduce the voltage with the variac. Unplug that variac from the wall, turning off the 15 and 5 volt DC power supplies. We're disconnecting bus ground from the U terminal. The load resistors are staying on the P terminal, P1 terminal. Now, what do we have? The V is the one we're going to test first, the V high side IGBT. Pin 3 is the gate, pin 4 is the emitter. Okay, there's 3, there's 4, connecting bus ground to the V terminal, plugging the variac back in, turning on the variac, the 15 and 5 volt power supplies. Look at that. The V high side IGBT is working. Alright, there's about 150 volts peak. Let's go up to 200 on this one. There's 200 volts peak. Light bulbs are fairly bright. Okay, I'm going to reduce the variac voltage. The DC bus is discharging. Unplugging the variac. Turning off the 15 and 5 volt DC power supplies. There's only one more IGBT to test. Disconnecting bus ground from the V terminal. And W high side IGBT. Pin 5 is the gate. Pin 6 is the emitter. Connecting bus ground to the W terminal. Plugging the variac back in. Turning on the variac, the 15 and 5 volt DC power supplies. Slowly increasing the variac voltage. 100 volts peak. 150 volts peak. 200 volts peak. W high side IGBT is good. Alright, all. Isn't that a fascinating circuit? That is two ways to test your IGBT. With your diode test mode with the meter, or by dynamically turning on and off each individual IGBT one at a time. Takes a little bit of effort, but you can do it. Hope you enjoyed that video. We'll see you in the next one. Afternoon all, here we are again at the house. Now we're going to first take a look at my simplified drawings of the IGBT that we performed the test on. Here is where you would connect the motor, U V, and W. Here's the P1 terminal, and here's the N terminal. And here are the gates of each IGBT. So up here we have 3 IGBTs on the high side connected to the positive DC bus. Down here we have 3 IGBTs on the low side connected to bus ground. When we want to test each individual IGBT, for instance, we want to test the low side IGBT here. We have our gate driver circuit connected to pin 8, our DC bus ground connected to terminal N, and our light bulb connected to the U terminal, going up to our DC bus plus. And when we turn on this IGBT, the current will flow from the plus bus through our light bulb load and down to bus ground through that one turned on IGBT. Now let's say we want to check the high side U IGBT. We would connect our light bulb load up here on the P1 terminal going to our DC bus plus. So light bulb connection to this IGBT, and then we would connect our U terminal to our DC bus ground, and then when we turn on this IGBT, current would flow from plus DC bus through the light bulb load through this IGBT back to bus ground. And we do that for all 6 IGBTs. Now I didn't draw the regenerative braking IGBT, but it would the test is the same as when we test this lower IGBT right here. We can see from my drawing that the gate on the high side and the emitter on the high side, they're all separate. They're not tied together. But down here on the low side, the emitters are all tied together. Here, pin 11 is tied to bus ground. Alright, let's bring up the next drawing, and you'll get a clearer picture of testing the high side and the low side IGBTs. Now what we have here is a circuit using a variac, a bridge rectifier, filter capacitors to make a DC bus. This is variable. We can vary that DC bus voltage as you saw in the video by rotating this knob up and down. Here is our U low side IGBT. Now terminal U is connected to 2 series light bulbs that are connected to the positive DC bus voltage. The emitter of that IGBT, the N terminal, is connected to bus ground. And our gate firing circuit, we'll see that in just a little bit. The gate firing circuit turns this IGBT on and off so that we were able to increase the voltage by turning this knob right here and testing that IGBT with these 2 light bulb loads right here. So this is the low side IGBTs. When we want to test the V and the W terminals, we move this red wire from U, move it to V, and then we changed our gate and emitter connections, and we were able to test the V and the W terminals. Does that make sense? I hope it does. I hope it makes sense. But what you need to make this DC bus is a variac that plugs into the wall. Here in America, we're 120 volts AC. The output of the variac goes to a bridge rectifier, and the positive side of the bridge rectifier is filtered with two 3300 microfarad 400 volt capacitors right here. The ground side of the bridge rectifier connects to the ground side of this lower capacitor. These are in series right here. When you series capacitors, the voltage will double, but the capacitance will be cut in half. So we could increase this voltage up to 800 volts with no problem. These bus capacitors right here would be able to handle that. Let's look at the high side IGBT. This drawing looks identical to the last drawing. What's different? Well, here we connect the collector of the U high side IGBT to the light bulb load. The other side of the light bulb load being connected to bus plus. And the U terminal is connected to bus ground. Well, it seems a little bit counterintuitive, but it works. Current still flows in the same direction through the IGBT to test that it's good, turning on these light bulbs. Now, let's go and look at the gate driver circuit that we put together on that breadboard. Now this is a very, very simple circuit. It looks complex, but don't let that worry you. What we have here is an NE555N timer IC. It is set up in astable mode. And what astable mode is that it will continuously emit a square wave on the output pin 3. Very simple circuit to breadboard right there. Connect the dots right here. Now the square wave that's emitted from the NE555N timer IC is passed on to this input LED of a CNY 17-2 optocoupler. This 560 ohm resistor right here is a current limiting resistor. You don't want to apply 0 to 5 volts directly to an LED because that LED will not handle the current. You have to current limit the resistor, current limit the LED inside that optocoupler. Down here is a green LED. It is just a visual indication to us that the 555 timer IC is emitting square waves. So this LED, when this point right here, pin 1, goes high, goes to 5 volts, we're powering up that 555 timer IC with plus 5 volts DC. When this point right here goes to plus 5 volts in reference to pin 2, that LED is turned on and it emits photons into the base of that phototransistor, causing it to conduct. Now this voltage up here, 15 volts DC, this is the gate voltage for that IGBT that we are testing. If your gate voltage is different, you change this voltage right here to match your gate voltage of that IGBT that you're testing. So when this transistor is turned on, this voltage is applied to the base of the driver transistor, tip 121, through this 20 kilo ohm resistor. When that tip 121 base emitter junction is higher than 0.7 volts, it starts to conduct, and so the output goes low. The gate voltage goes low to bust ground through the collector emitter junction. When this point right here is at 0 volts, that LED is turned off, and thus the phototransistor is turned off. And now the base is pulled to ground. Since this is not conducting, the base is pulled to ground through this 10 kilo ohm resistor, turning off that transistor. With this transistor off, now the gate voltage is at plus 15 volts through this 1 kilo ohm resistor. So by continuously turning this LED on and off and on and off, this transistor will turn on and off and on and off to ground through the transistor, to 15 volts through the 1 kilo ohm resistor. And that's how you drive the gate of the IGBT under test with our circuit right here. Now this is a fascinating IC right here, this NE555. And you can study that a little bit more. I actually think I have some videos explaining the 555 IC somewheres. I have to go back through the history and check that out. And what's the purpose of the optocoupler? Well, here we're powering up our plus 5 NE555N with plus 5 volts DC. But we want to drive the gate of that IGBT on and off with a peak of 15 volts DC, 0 volts to 15 volts, 0 volts to 15 volts. This is performing a level shift from a 5 volt square wave to a 15 volt square wave. And that's the purpose of the optocoupler in our circuit. Now in a drive, gates are turned on and off with optocouplers and driver circuits. Their main function in a drive, like an inverter drive or a servo drive, the optocoupler circuits are to prevent a catastrophic failure on the high voltage side from coming back and smashing the microcontroller, the processor side of that servo or inverter drive. And you see it all the time. An IGBT will short and it will explode, and all of that catastrophic energy never is passed from the high voltage side to the low voltage side. So when your drive power side fails, the brains of that drive are still functioning. And that's the purpose of the optocouplers in an actual drive. Did I leave anything out? I always construct these drawings and explain these drawings, and I always leave something out. It never fails. So y'all let me know if I forgot to mention something. But there you go. There you go. Not a difficult circuit to breadboard. Just be careful with those voltages out there that variac creates. Don't get across those. That'll make for you a bad day. Okay. All right. I'm going to go in the backyard and water the chives and the basil, and then cook me a little bit of dinner here in a little bit. Have you a good day, all. Enjoy the time with your families. Your time is short. And catastrophic events come up on you real quick without any foresight. Oh well, that's that. Come on, let's get out of here.